We'll start because we need to finish on time. So it's a pleasure to introduce Jure Zupan for our special seminar, and thanks very much for coming up on Easter Monday. Yes. Jure has got his PhD in the University of Ljubljana some time ago, and after that he was several postdoctoral appointments at Technion in Israel and Carnegie Mellon in the US. After that, he secured a faculty position back in Ljubljana, but soon moved back to the US to the University of Cincinnati, where he rose to the ranks of full professor. Jure is known for a variety of contributions to field of theoretical particle physics. He works closely in collaborations with experimentalists as well. He has distinguished himself in papers that pointed out how to determine one of the important angles of the Cantilever-Kobayashi-Maskawa matrix, so-called gamma angle, and he has now established himself in the field of dark matter and dark sectors. For that,
Well, thank you for the nice introduction. So what I'll talk about is focus on how to search for new physics using rare lepton transitions. It's based. Oh. Not sure what it is. Ah. So is it better? Okay.
you can flip it.
Oh. Sorry about the noise. It's based on a series of papers in the last few years. Some of them were done also with people in Minnesota. Now, before I go into the actual topic of the talk, I just want to flash some other topics that I work on since I'm talking to people during this visit. So one of the, I would say there are three kind of areas where I'm spending my time on. The first one, Maxime already mentioned, it's flavor physics, and lately it's rare lepton decays that I will talk about. So there's this thing. And then rare Kern decays, non-standard neutrino interactions. Amazingly, I still have a project on this CKM gamma extraction, which has to do with how you use machine learning to do that. There's another quite a lot of time I'm spending now on thinking about the hybridization, how you can describe this using machine learning or improve our description, or if you want parametrization. And here, this is with PTO people. And then dark matter, dark sector. So I think the first one will be maybe out is the heavy dark matter EFT. There is a project on the dark gauge fields and the cosmology. Inelastic nuclear transitions, how you could search for dark matter using that. The atomic transitions and new physics. All right, so that's kind of the advertisement of all the stuff that you can ask me and we can chat about. Let me now come back to the topic of the talk, which is, I said, rare lepton transitions and new physics. And here it's either muon decays or the tau decays. So the muons are the lightest unstable particle. So it means that it's relatively easy to produce. There will be big samples. So you can search for rare decays just because you have huge statistics there. Taus are heavier. So they're interesting because it's a copy of a muon, but a heavier one. The flip side of this is that it can decay in many different ways. So there are many modes that you can search for. So if you find a deviation, it also means that you will have more handles to learn about the structure of the UV. There are kind of two sides to this. You can use muons and taus to search for heavy new physics. And there's also, you can search for light new physics, and I'll just spend a few transparencies on each. So the heavy new physics is you have heavy intermediate particle, you integrate it out, and you end up with an effective operator. These are what's plotted here are the are dimension 6 operators, a particular chiral structure. And what you see are different indirect measurements that you can do. This is with the kaon system or the quark system, kaon system, the B and B sub S. We will be interested in these blue colored columns. So the 3 mu to E gamma, mu to 3, mu to E conversion are the classic golden channels. And here there's also a tau to mu gamma scale. The more dark colored columns tells you the improvements expected. Okay, this is from 2019, but I like the colors. So you see on the log scale, we expect a huge jump in sensitivity because new experiments are coming online. So that's an interesting place to be. And then the rest is, for instance, the CP violating observables, the Higgs decays, top decays, and then direct searches by producing resonances on share at the LHC. All right, so I spent time talking about the muon, the tau decays. I said also that there's something new happens if you are able to produce light new physics on share. So the parameter space that we're probing when you have these heavy modes that you integrated out looks something like this. Is either the mass of this thing that got integrated out is very heavy. That means that the couplings also need to be big for you to see an effect. If it's light, then the couplings need to be lighter. So that's this line here, no? So I live on this line. Now, if you're able to produce particles on share, this new guy, so you're somewhere down here, something qualitatively new happens. And in fact, I can translate this to a parametrically enhanced sensitivity to new physics. So let's see why this happens. Let's take a few examples. Let's say take a kaon to pion plus a light particle, or muon goes to an electron with another light particle. Well, these are probing very high new physics. If, of course, we get lucky enough that something like this exists, that it's a light particle. This parametric gains is just because the standard model rate for the muon decay is heavily suppressed. It's suppressed due to being a weak decay, means that the decay width of a muon goes as 1 over W mass to the 4th power. I have an intermediate W gauge boson. You integrate it out. The propagator is 1 over W squared. The matrix element is this thing squared. So 1 over MW to the 4th power. I have to make up a dimensional quantity, so it will scale like the muon mass to the 5th power over MW to the 4th power. Now, if you convert this, let me go down all the way down here. So if you convert this into the case where the mu to E plus a light guy, now I change the notation from X to phi, is through a dimension 5 operator, so it's suppressed by only 1 power of this new physics scale. Well, you see that now this branching ratio will have only 1 over FA squared instead of MW to the 4th. So the branching ratio compared to the standard model rate has also 1 power, so 2 powers of the muon mass. So there's this parametric enhancement, this FA, which is the new physics UV scale. You see that just because I'm comparing this with a heavily suppressed standard model rate, I will be able to gain sensitivity to very high scales. So you're probing a different type of operators, and why you're able to probe this is because you are able to produce these light particles on share. Now, I had 2 comments here more, so there are 2 more statements here. One is that, of course, if this coupling to light degrees of freedom itself is through dimension 6 operators, well, this parametric gain disappears. if, so here. And if it's dimension 4 operator, it's there, but I cannot translate this so easily into a UV scale. It's a dimensionless quantity. So you see there's huge parametric gain. There's some dimensionless parameter, but if I talk about scales, it's much more difficult for me to just compare so easily. All right. So the upshot is, if I look at the decay widths, the standard model decay widths of the leptons, which are in red, and the hadrons, well, they scale, as I said, as the mass of this object to the 5th power. Roughly, there's a scatter because details matters, of course. I will talk about the muons and the tau. So they live at, they are quite different. They have quite different decay times. This guy decays, tau decays much more quickly. And this will also translate into different sensitivities to UV physics. All right, so what will I do in the rest of the talk? I already see that probably I have to be quick on some of them. So I'll split the talk into 2 parts. The first one will be about heavy new physics. I have few slides on the classical charged lepton flavor violating observables. The rest of this part of the talk will be about effective field theory based predictions for mu to E conversion. And then there's the second part where I will just give you like 1 slide on each example, and I will point out the sensitivity to heavy scales, this UV scale. So the first one will be flavor violating QCD axiom. There I'll say I have 1 slide on time-dependent searches, the exotica. So it's exotica muon decays into the slide states, and then the same thing for the taus. Similar story. All right. So the first part, it's about the heavy new physics, searching for heavy new physics with the muons. So there's a steady progress on these 3 golden modes, so mu to E gamma, mu to E conversion, mu to 3E. What's plotted here are the limits on the branching ratios or the normalized rates for the mu to E conversion. They're color-coded, as you see, and there's on the exponential, on the log plot, you can see big gain. And then there's this corresponds to different technologies. So first, it was just looking at cosmic rays. Then you started using pion beams. The pions decay to muons, so you can also stop muons. And you see this is the promised progress with the new experiment. So that's why this is interesting, is again, hopefully we can catch up with this log or exponential increase in sensitivity. All right, these are very rare processes. We're talking about branching ratios of 10 to the minus 15, 10 to the minus 18. Now, if I do something like I say, oh, maybe I want to use the cosmic rays as in the 1940s, and I had an experiment, palm-sized experiment, well, I would have to wait more than the age of the universe to collect this many muons. So clearly, of course, you want to go for a facility. All right, so there are several of these experiments. They are that are either running. So MEC2 within 2 weeks or so will present their first results. Each of them is built for one of these golden channels, so mu to E gamma. The mu to 3E will be also at PSI, which is in Switzerland near Zurich. But it will be engineered to search for the mu to 3 electrons, so mu to 2 positrons plus an electron. Then there's the Fermilab mu to E conversion, which is here in the US. There's the equivalent effort, similar effort at J-Park in Japan. So this is about the muons. Then for the taus, you can you can search for this rare tau decays at LHC or at Beltus, which is an E plus E minus collider in Japan. Right, so it's a global effort. I've mostly talked about the muons here. There are all these three golden modes, they probe different types of physics. So what's plotted here are different dimension 6 operators. For instance, if you have only leptons, I didn't put the labels, but one of these is muon and the rest are electrons. So this would be a mu2 3e left-handed current. Or if I switch left-handed for right-handed, all of those are probed by mu2 3e at 3 level. If I have quarks instead of leptons, well, that's the mu2e conversion, because quarks know about the nucleus that this thing converts in the field of. Or this is above electroweak scale, so you can have lepton-Higgs operators where this will project out the coupling to the Z. There's one set of operators as all three of them are sensitive, and these are the dipole types. So you'll have a mu2e transition. Above electroweak, this will be either the Z, so either the W3 or the hypercharge. If once you break the electroweak symmetry, oh, you have a question. Yes.
Yeah, outsiders. All these operators are outside of standard model.
Yeah, oh, yes, okay. So these are, you have new physics, thank you. So this is, you have new physics, you integrate out stuff, and you interpret this is all outside the standard model, and you interpret the deviation from the standard model in terms of these extra terms in the Lagrangian. They are dimension 6 because you assume that you will not produce any states on shell. So they're always integrated. These are point interactions, and they're described by either having standard model fermions like mu2 3e on the external legs, or in this case, it would be photons, or if you're at high energies, it would be W's. So the Z and the photon. So maybe, yeah, thank you. I should have said this more clearly. All right, but so you can turn around and say, so let's say we pick these dipole operators. At low energies, the W and the B, you will only see the direction that is mu2e gamma like, but all three experiments can, all three types of experiments are sensitive to these dipole operators. So you can now compare the sensitivity. The mu2 3e will be directly proportional to the mu2e gamma, where the mu2e gamma is just converts, there's a Dalitz conversion. So an off-shell gamma goes to E plus E minus, and you have the mu2 3e. That's this log enhanced piece is just the phase space log. The mu2e conversion, you can just estimate that this is roughly the electromagnetic fine structure constant times the branching ratio of mu2e gamma. So what's plotted here is the dipole operator, which now I just took this photon direction from present limits in some normalization. So that's this dipole operator, but now only the photon piece. So I have mu2e gamma, where either I have an on-shell photon that you see, or you have a Dalitz conversion. So photon is off-shell and creates an E plus E minus pair, or photon talks to the nucleus and does the mu2e conversion. So this is the further out you are. So this is 10 to the minus 8 all the way 10 to the minus 12 in some normalization. Yes. Yeah.
The things you're saying are model dependent, meaning we talked about sort of light particles, synthetic particles, and which are just experimental constraints.
Yes. All right. Very good. So if you assume that you have new physics that generates mu electron photon coupling, all right. So and this is the only thing that's the only new physics coupling that new physics induced effect that you see at low energies. All right. So it's a very model dependent statement. But so if you're in this very peculiar part of the parameter space, then you can compare the sensitivity of three types of experiments. So the punchline here is, yeah, so and I'll comment again. No? So the punchline is this red shaded region is the present limits, means that further out you are, the less sensitive these types of experiments are to this type of new physics. So you see mu to 3e, mu to e conversion are less sensitive than mu to e gamma than the experiment that is built to search for this type of new physics. All right, that's the present status. And again, this is for a very kind of narrow part of parameter space. So there are many models. This is super model dependent statement, but there's one type of models where you can really compare the sensitivities of these three experiments. Now you go into the future, the mu to e gamma searches, so the ones that are built for this operator, there's only a small improvement. So that's from MEC to MEC2, while these other ones, there's a huge jump. And now you see, so that's the punchline, is that there is a technical issue, backgrounds, with the mu to e gamma searches, while these two other ways of probing this type of new physics have ways to go. And if you go to the next phase of this experiment, they will push even further out. All right, so it's a model-dependent comparison, but the punchline is that there are two types of experiments that will have huge gains, while there's one where you would need to change the way you're doing things. No, I mean, that's would be a very costly thing. You could do it at Fermilab. I mean, I can talk a bit more about this, but that's the punchline, is that there are two types of experiments, have bright future. The third one, we're gonna run into the systematics. All right, yes, go ahead.
Future prediction work together to form an equilateral triangle.
Yes, it's amazing, no? How you fine-tune this sensitivity.
Do you have such triangle plot for other?
For the other, no. I mean, I stole this from this review, which is now quite old, but it's about projections. Yeah, no, they didn't do it for the other ones because there's no overlap at 3 level. No? I mean, also what it's 3 level, but you could do it for the Z exchanges, right? But I mean, you already know what the answer is. The two types will be sensitive in a similar way.
So based on that table, it seems like there would be a complete use case for mu to e gamma is this operator, and you're now saying that this operator, the other two experiments, I think he has mu to e gamma.
Yes, that's the punchline. Yeah. Well, okay, so to do mu to e gamma search.
Yeah.
Well, if you see something, I think then you will have a strong motivation to invest money, because there are not that many things that you can measure. I can comment about this a bit more. So now I want to go to the predictions. So I motivated, so far, what did I do? I motivated why mu to e conversion is a very interesting thing to look at. It will be very sensitive, even in this limited case where you have designed experiments to search for mu to e gamma, you will have the same sensitivity, right? And there are also many operators, so many types of new physics that you will be sensitive to. So it has to do with, of course, now if you couple to quarks or if you couple to gluons, but that's higher. So the rest of this part of the talk is about predictions. So far it was just motivation. So now what did we do? No? So there's so what we do was we provided this effective field theory based prediction for mu to e conversion. The main assumption is that there's heavy new physics, but you can even relax this. No, it's really not a big deal, but it's easier to think about this as the new physics, and then there's an open source code that does the predictions for you. All right, so why you can do calculations here? There's a series of there's a hierarchy of scales. Now, what is this process? Is you stop a mu minus. This gets trapped in the 1s orbital of the target atom, in this case, aluminum. And then what you're looking for is a mu minus that converts to an electron. So you have a fast-going electron. and the aluminum takes the recoil. So aluminum is a very, very heavy object. So it will take a very small amount of kinetic energy, and it will take over the recoil. So what you have is a monoenergetic electron, which is almost insensitive to the mass of the target. So this is the mass of the target. You see that it cancels out. If I have something very, very heavy, no matter what target I use, this is almost always just 1. The Q squared is the momentum exchange that flows into the electron. It's the kick. And this will be order 100 MeV, so the mass of the muon, up to, let's say, 5% if you change your target. So you will always probe the same momentum exchange of order 100 MeV, 105, 107. Yes?
So aluminum here is in a crystal or it's a free atom?
Oh, as far as I understand, it's just aluminum, you know, the metal, no? So there's no crystal, real aluminum. Yeah, plates. Well, there's a target, yeah.
Okay.
Yeah.
So it's not in collider.
No, so what you do is you have a muon, it stops in this target, and then you wait. Yeah.
So the recoil goes to the crystal, not to the single atom.
No, it goes to this, there's no crystal, so it's just aluminum. Oh, sorry. It's
This aluminum is in a zone crystal.
yeah, the metal. Yes.
Instrument things to find this very fast.
So you don't see this. You don't see this. So if you are worried whether this goes into phonons or I have aluminum, like atom that gets kicked out, maybe that was the question. Yeah, so this part you don't care about because there's no phonon detector, you don't measure any increase of energy, nothing, no? All you see is this huge kick to the electron that comes out and you search for this 100 MeV electron. Yeah, okay. So 100 MeV, so that's important. The 100 MeV is smaller but comparable to the QCD scale. So that's why you can do predictions, and it's comparable to the typical momentum of nucleons and protons inside the nucleus. All right, so I said there's a number of scales that enter here, and there are corresponding effective field theories. So that's the heavy UV scale. You integrate out this mediator, end up with standard model effective field theory. So this was this dimension 6 operators that I was showing a few slides ago. What got integrated out were the heavy degrees of freedom. So the Z boson, the W, the Higgs, and the top. Once you do that, you end up with a weak effective theory, which still has 5 quark flavors, the gluons, the photons, and the leptons. And you lower this scale. First, you hit the big quark mass, which is at 4 GeV, the charm quark mass at 1.3 GeV. Then there's the non-perturbative scale, and this is where, so this is what's in the muon bridge code, and what we calculated is this part. No? So you are now in deep non-perturbative regime, but still you have an expansion parameter, which I'll talk about. So you can use a chiral perturbation theory expansion, and this is very hard to read. And there's nuclear response functions at the very low end. So I'll talk about these ingredients and this code as the corresponding code or elements that do different things. So this will have a part of the code will know about the nuclear response functions. The other one, which is this part, will know about the chiral expansion, and then how you talk to the higher scale is in this other part of the code. So it's modular because these types of problems you can also use for other physics. All right, so let me talk a little bit about how these operators look like. So we'll start with the weak effective theory. We work up to dimension 7, including dimension 7. So these dipole moment operators are already flashed. So there's 2 types with a scalar current, so scalar tensor current, or the the one that has a gamma 5. If this were not flavor violating, this would be CP even and CP odd type operators. And this is the photon, So mu to E photon at dimension 5, there are two types of operators. And then these dimension 6 operators that I flashed already, but let me just point out. So there's 10 of them. There will be also tensor operators, which I will comment on in a second. There's scalar type operators and then vector currents. It's important. This structure is important because you take non-relativistic limits. So these different operators will have very different behaviors when you go to low energies. And then there's additional 16 operators that I want to show that are dimension 7, right? Now I have a comment here. These tensor currents, maybe this is for people that are more used to the SMEFT. This appears now at dimension 6 already. All right. So what are these scales that help us with the calculation? So the first one was the velocity of the outgoing target of the nucleus is completely irrelevant for the problem. So you can ignore what the aluminum does. Or so this is you can work with so 0th order in this expansion parameter. There's a bound muon velocity. For aluminum, this is a non-relativistic system. So we work to the first non-leading order, so up to linear order in this V mu. This Vn is the typical velocity of the nucleons inside the nucleus. So this would be of order 0.1 in the speed of light units. So this is comparable to the muon velocity, but maybe a little bit bigger. And then there's this nuclear scale. So the B bar is the typical size of the nucleus. The momentum exchange is comparable to the inverse size of the nucleus. So that's order 1 parameter, and you need to keep this to all orders. This will be the nuclear response functions. All right. The other two, you can expand it. So there's Carl effective theory, where you expand in the nucleon velocity, and the end is just that you will only interact with a single nucleon inside the nucleus. Right? So where you interact at the same time with two nucleons, it's suppressed in this Carl counting. Right? And we go to linear order. Now, what you end up with is a set is an effective field theory where you have now non-relativistic operators. So, for instance, this Y1L, Y1N, this thing counts the number of neutrons or protons, N can be neutron or proton. And this 1L would be a number operator if I had a mu current. Now I have a mu E current, so it's a slightly more involved thing. For people that have worked on dark detection, this should look very familiar, except that there's something called a Q hat here. This is now just a direction into which the electron goes. In dark matter direct detection, this was the momentum exchange between dark matter and the target. Right? Otherwise, it would look very similar. The primes are where the differences are if you were to take Q hat to be Q vector. Right? So I apologize for people that are not experts. It's not super interesting to scare this stuff. But I want you to just see visually that there are many operators that in principle you need to take into account, because I have a graphical picture where you will see that this thing really populates all these operators, and it's a zoo. So at the end of the day, you're very happy that somebody put a code out that does this for you. All right, so what's next in this prediction is I have this non-relativistic effective theory Lagrangian. So all the ingredients are non-relativistic. The muon is non-relativistic. The neutron and proton are non-relativistic, but there is an electron that is ultra-relativistic. Now, the coefficients in front are in principle function of the momentum exchange, but this momentum exchange is just almost a number. No, it changes by 5%. So basically, even though this strictly speaking is not an effective field theory, it is for practical purposes. Now I have if I have a propagating Jure freedom, which is Q effective, that would be like pions, it will still always be a coefficient. Maybe I'm mumbling a little bit. All right. So what are these coefficients? Well, they need to know about the weak effective theory operators where I have currents that are sandwiched between the neutron and proton elements. So N is either neutron goes to neutron or proton goes to proton. So this will have kinematical, we will know about UV, so the SMEF, these Wilson coefficients, the form factors. There's each of these currents has corresponding form factors. So most of this you can get out from lattice. Some of them you need to write dispersion relations for. That's in the details. And it boils down, all this structure boils down into one, for instance, a coefficient that you measure, and this is the one that is, for instance, coherently enhanced. So what you want to take out of this is that even though there's a lot of structure there, there's actually not that many things that you will measure at the end of the day. All right. Why? Well, because it's hidden inside nuclear physics. So there will be a matrix element squared will get encoded into the response of the nucleons. They have a name. So this is the nuclear response function, but they have a very hierarchical structure. There's, if you are counting the number of neutrons and protons in these relatively low momentum exchanges, this will get coherently enhanced. You see the whole nucleus, it gets squared. So that's why this is of order A squared. The name for this is Wm, doesn't matter. Then you either know about the spin of the nucleons inside so the nuclear spin, longitudinal or the transverse one. And then there's this surprise maybe, which is these tensor currents at next to leading order, they get coherently enhanced over half field shells. All right. That's why you needed to go to next to leading order to capture this piece here. And then the rest is much smaller. So basically, you only have 4 types of nuclear responses that get probed for neutrons and protons, so in reality 8. And that's it. These are the numbers that you will measure. If you have a new physics that you see, there will be 8 numbers that you will measure, and then you try to deduce as much as you can about the UV. All right, so how does this look like? So that's the color coding that I promised, is that these are the response functions. They're color coded by the coefficients inside the non-relativistic theory. So if I pick one Wilson or one coefficient, it can either have several or one responses. So this will be C12 can go here, but also the C3N will give me these tensor currents responses. They can come from different heavy so the UV physics. So that's the colors. If I switch on one Wilson coefficient at the weak scale, it will populate C1. So let's pick this one on C1. It will populate C4, C6. So you see that, I'm not really explaining the physics because there's a lot of moving parts here, but what the visual imprint is that you see that it will be very hard to solve the inverse problem. Now I will measure very few numbers and I want to go up, and this will be very hard. The other thing is you go from the UV physics down. Okay, it's just complicated. It's hard to keep track of all these moving parts, but of course that is doable at least. All right. So I'll show you one example, and I think I will just give you the punchline for the rest of the talk because I should really finish on time. So I picked a random example. There's a leptoquark that gets exchanged and creates mu to E conversion, and it also couples the quarks. As the Lagrangian, it's not so important. The important thing is that it was picked such that it generates all these 10-dimension 6 operators, right? Including the tensor currents. And then you turn the crank, you put in a random point. You want this to be as representative as possible. And you look at what the contribution is from different nuclear response functions for mu to E conversion rate. So the spin independent pieces are, as you would expect, it's completely dominated by spin independent, because that's a random point. You're not killing this coherently enhanced E squared enhanced piece. And then more interestingly is that spin dependent and tensor currents you see are of a similar order. So you really needed to include the subleading piece if spin dependent forces are important. Now, if you picked a different example, maybe the spin independent piece is canceled, could be just a coincidence, so there's a model. But the punchline is the subleading pieces then become important, the things that you would maybe ignore if you're not careful. All right. So I'm basically done. Yeah. Yes.
It's very impressive thing that you put together for the new physics.
Yes.
New physics, so far, we have consistent with zero.
Yes.
Maybe it will stay like that.
Right.
We don't know, right? But important things that the new background level, right? Because the success of the experiment will ultimately depend on whether the backgrounds are calculated properly. I know that people have addressed muon decay in orbit when the electron is infinitely, well,
Yes.
energetic. But there will be also effects with the radiative muon capture where neutrino is not energetic, right? But the photons are, very energetic. Is this being treated to the same level of rigor, or because I think it's more one thing of your input, right? So
Yes.
radiative muon capture would be probably one of the super important backgrounds. So
Right.
we've seen it.
Yes. No, I agree. So first of all, I don't know the literature well enough to answer this with authority, no? But I do worry the situation may be similar to what the situation was here, that there was no systematic, I did not talk about, there are different approximations that were done for mu to E conversion that now were also included systematically. You can do different things, no? So you could build an EFT. I think this Chacon is doing this at Brookhaven. So he did the first step where he started building the program. So you could resum the soft photon exchanges. Okay, the problem is it's not okay. I don't really know whether you will run into problems or not, because you might be secretly doing a partial wave expansion when you do that, and you should not do that. I mean, if you want to have a precise prescription, that to be seen, I would say, not to be seen. I think it's a good problem to look at. Yeah.
Anyway, the general question is
Right.
when you enlarge your box, you have to be able to describe the.
Absolutely, yes.
The,
I mean,
the next to signal reach.
right. So I will show just one plot out of this second talk, part of the talk, which will drive home the message that I was harping, which is I'll talk about QCD axion. So it will be 2 slides and then I will be done. All right. So I thought I have to finish at 1, no?
So I have 15 minutes.
Ah, fantastic. Okay, then I misread.
Let's say 10 minutes.
All right, sure. Okay. Then maybe I will go back and at least say what's on the slides. All right, so I'm switching to the second part. Can we search for light new physics? Now, there are these huge data sets that will be available in principle. So many muons will get created, will decay, and then part of or all of the what will be measured will depend on the experiment. So whether or not you can use these large data sets to search for something that these experiments were not built for, no? For instance, for mu2e, the big problem is that a lot of the interesting part of the parameter space lies where the backgrounds are huge, so the detector is built on the hardware level such that it kills this. No? So it will kill the light new physics signal. No? So I said that I'll show 3 examples, but maybe I'll just really focus on the QCD axion one, which is mu2e. A is this light particle, the axion. The same for tau to mu e plus an axion. Light here really means well below the electron volt. I think you had a talk about the time-dependent mu2e similar types, but this would be one of the dark sector particles. The mu2 VE is work with Maxime, so have a local expert that can tell you everything. So I'll probably switch this. I will not talk about those. And then there's beam dumps that, again, I'm working with Maxime for rare tau decay. So there you search for displaced tau to mu plus a light particle. And this guy, for instance, decays to 2 muons, but this is 100 meters away from the interaction point. All right, so I will just talk about the QCD axion, and then I'll go to the conclusions. I will skip this part. I'm happy to talk about it often. All right, so the QCD axion, why do I talk about this? Because I think it's out of those is maybe most motivated in the sense that all you need to do is I take spontaneously broken global symmetry. So I have a pseudo Nambu-Goldstone boson, pseudo. If this were not broken explicitly, this light particle would be massless. Now you can have explicit breaking or through anomalies so that this is not a true symmetry. If light enough, it can be dark matter. And also, it can also solve the strong CB problem. So it's a well motivated from several sides. If you look at the most general model, this at low energies will induce couplings of QCD axion to gluons. That's necessary for you to solve the strong CP problem. FA is the UV scale. So that's where this global symmetry gets broken spontaneously. For us, this will be 10 to the 10 GeV. It could be 10 to the 12, 10 to the or higher. It will couple to photons almost inevitably because it couples to gluons. So unless you have a freak cancellation, you will have a sizable couplings to photons at low energies. And then you can also have couplings to standard model fermions that are now derivative operators. The derivative operators, because these are Nambu-Goldstone bosons. They have, this can be quarks or leptons, and they will have so diagonal and off diagonal coupling. So you could have mu2e with vector or axial couplings. What these experiments will be sensitive to is either the vector or an axial structure, again, depends on the details, but quite often they will just be sensitive to the sum squared, all right? Okay, so this, if you see a capital F, it just means that these coefficients were absorbed in the definition of this effective UV scale. All right, so as I said, ARPs could have these flavor violating couplings, and the surprise is that these experiments are sensitive enough that you are, if all these couplings are, let's say, order 1, and I'm only switching on the couplings to leptons, there will be bounds from astrophysics that will be from the couplings to electrons, so diagonal couplings. They would have increased the cooling, so the leak of the energy out of the astrophysical objects, for instance, the white dwarf, or the red giants, or the supernovae. So this is if you say that it couples only to electrons. This would be if it would be the bound if it couples to muons. It has, so remember, large scale means small couplings. So on this side, for instance, here, you just don't produce enough of those so that it would matter for the effects in astrophysics. There will be a lower bound here because you produce too many and they get trapped inside the object. And these are the current bounds from the mu to E decay. So mu to E to an axion. This axion you don't see, you see as a missing energy. So this is twist from 2005, and Eudidio et al. Is from 1985. All right, so very old experiments. There's a reason why they differ. One had polarized muons, and this had a much less polarized one. And these are the projected sensitivities. So the mu to EX this is our labeling of engineering run of mu to E. So a calibration run for 2 weeks, where instead of mu minus, you use mu plus, and you would have world's best limits. All right. But you see that these scales are enormous, no? So this would be an effective scale of 10 to the 10, and it's above the astrophysics reach. You can also map this onto the QCD axion plots. It's completely orthogonal. It will probe a different part of the parameter space. You may or may not see something in the photons. For this, no. This is a completely different regime. Yeah. All right. So I said I will skip all the rest. I think part of it you heard talks on, so I didn't want to. Sorry. All right. So I just said the conclusion. So I spent most of my time talking about this effective field theory approach for predicting the mu to E conversion rates. There's this public code, muon bridge. And then I spend just a little bit of my time on the rare muon decays. Similar story, but same, but different for the tau decays, which can be used for light new physics search. There's this parametric enhancement to UV scares that we saw, and I covered the QCD axion, which would be kind of a very funny thing to discover a QCD axion, because it would couple to leptons, but you could be the most sensitive probe. It's very easy to build models where this is true. This is a very, very model-dependent statement. No? Then you would need to also show that this is a QCD axion. All right, thank you very much.
You mentioned Plessinger's problem. So you measure 6 or 8 numbers. So how do you reconstruct UV physics out of this?
Very good. Yes, that's an excellent question. And there is, I think, so, okay, so there's a big asterisk as to what they said, no? Is that, so we have something to look at. I had this one. Let's look at this. All right, so if you can, so this will be, let's say, be very optimistic. No, so we see the signal, we put many targets in, so you change the target. So what do you want to change? Now you want to change the proton content, the neutron content. So that would be relatively easy. I just need to take lighter versus heavier elements, and I'll get a decent change in the proton versus neutron content. You want to pick different spin, so targets that have different spins. So this should also be relatively easy, no? So this would cover these 8 response functions that I talked about. No? So you would pick many different nuclei, and then you will end up with these 8 numbers. After that, it becomes hard. So the way you could make progress is it becomes hard on several fronts. So one is you need to calculate more precisely the nuclear physics because you want to be sensitive to the subbleeding effects. And you remember here, so everything here is up to this subbleeding order where you're not A squared enhanced, no? So you want to be down here. So that's first hard problem is in principle doable, no? So if you make a big progress in nuclear physics, you could solve this. There is also an alternative, which is that you go for the inelastic transitions. So the problem there is more experimental. So what we would do is you could be sensitive for the case where muon excites the nucleus, right? So you go to some higher resonance of the nucleus, and then you look for the decay product of that nucleus. So this will be sensitive in a different way, very different way, to these operators. The problem there is experimental because now this trick where you have an electron which is very, very precise, at the highest energy, now you pay a price because you excite the nucleus, the electron that comes out is less energetic, the backgrounds are bigger. So that's then it's easier for the theorist, but it becomes harder for the experimentalist. So if there's a signal, we'll probably do, in principle, we can do much better than what I was telling you, but it will require a lot of work. You can do it, like you can do. There will be an additional problem when you go to heavier, very heavy. Let's say that you want to do xenon instead of aluminum. This approximation of non-relativistic electron will not be a good approximation anymore. So this will be also a very hard problem. So if we see a signal, there will be a lot of fun for the theorists that are. So I'm taking out of this. Yes. Yes.
So in the head of this case, I think you said that the electron should be mono-energetic, like basically it takes all the energy. So
For mu to E conversion, yes.
So in like mu to E axion, in the axion case, then basically E will get half the energy.
Yes.
So roughly
Yes.
do the experiments look for mono-energetic signals also like half the problems as well?
Yes. So this is question because it also depends on what you're doing. No? So you go straight to the problem. So this would be mu to E nu bar. So let's say that this is the energy of the electron or positron that comes out of it, and this is the differential rate. All right. So this looks something like this. At leading order, it will look like a much more steep thing, and it gets smeared out because of the radiative corrections. All right. So now, where is the QCD axion? It's here. So you have a line here. So you have to search for a line on a super steep falling background. If it's somewhere else, like here, it's a much easier search. So the searches were done. Okay. There are tricks. You can pay an extra photon emission price, and then you don't see it on this steeply falling background. If for mu to E conversion, the decay is in orbit. So the mu minus is being used. This gets trapped on aluminum. So there was this ionic atom that we formed. Now, the problem is, so this decay in orbit for the two-body decay looks something like this. It gets smeared out. So this peak, be a line, or here, gets smeared out because the muons are in orbit, but they're not at rest. And this is the same thing, but the standard model rate. Okay. Now, how and the mu-to-E conversion would be a peak down here. So this is 100 MeV energy of the electron. This is 50 MeV. Right. The experiment itself is built to just be blind to all these electrons that are too soft. And that's why I was talking about the calibration run, is because then you run with a mu plus, and you measure this Michel spectrum. So you measure this Michel spectrum, which has a well-defined endpoint. This would be your calibration. It's not the only way you do the calibration. No? So if they decide to do this calibration run with the mu plus, then you would automatically be able to search for the QCD axion. And with 2 weeks of running, you're the best. No? So it really depends on. So it was a very good question with a very involved answer.
Very glad to finish at this point. Thank you very much, Jure Zupan.